In this video, we'll discuss dislocation arrays and boundaries. The figure on the left is from the last slide of the previous video when we discussed the dislocation multiplication. Here is the dislocation source, and dislocations coming from the same source will lie on the same slip plane, which forms the dislocation array. The TEM micrograph on the right was taken by a PhD student in our department, Cesar Pickett, in Professor Karaman's group. In this TEM image, you can see one dislocation arrays in a deformed high-entropy alloy. Since dislocations coming from the same source, they have the same Burgers vector, and they lie on the same slip plane, so they will repel each other, giving you the space between each dislocation. A natural question to ask is, what if we have a lot of dislocations not on the same slip plane? Before answering this question, let's look at something we have already learned, the forces between dislocations not on the same slip plane. If we have two edge dislocations of the same sign, then the most stable configuration is to have those dislocations stacking on top of each other. If the two edge dislocations have different signs, the most stable configuration is to have them 45 degrees apart. To simplify the model, we'll only focus on the first case. Please bear this in mind, it will become useful later. Now, consider a scenario. We had a metal bar, and we apply a bending force to deform it. In order to accommodate the shape change, a lot of dislocations will be generated. And there's a specific name for those dislocations called geometrically necessary dislocations, G and D. We can rearrange these dislocations to a stable configuration, having those same sign dislocations stacking on top of each other. This will give us a dislocation boundary, and more specifically, this is a symmetrical tilt boundary. We can make the scenario slightly more complicated. In the case on the left, we only considered Burgers vector of one type. What if we have two types of Burgers vectors, one pointing to the right, one pointing down? The vectors are B2, B1, B2, B2. This also gives us a tilt boundary, but with 2 degrees of freedom, while the example on the left gives us 1 degree of freedom. The next question to ask is, can we quantify the misorientation caused by dislocation boundaries? The equation is b over 2d equals to sine half theta, where b is the Burgers vector, d is the spacing of the dislocations, theta is the orientation difference. Here is one example of the spacing of two dislocations. From the simple expression, one can tell larger b and a smaller d can give larger theta. Also, if theta is sufficiently small, then the expression can be further simplified to b over d equals to theta. Let's put some numbers in. If the dislocation spacing is 14 nanometers, the Burgers vector is 0.25 nanometers, then the misorientation angle theta is 1 degree. We can also translate what we learned from those edge dislocations to screw dislocations. The example on the left shows the atomic positions resulting from rigid rotation, where the empty circles showing one crystal and the solid circles showing another crystal. To remove such abrupt change, as well as to accommodate the mismatch, one can introduce screw dislocations to form a dislocation boundary, and the resultant boundary is called a twist boundary. To do a quick summary, if you have a stack of edge dislocations, you'll get a tilt boundary. If you have arrays of screw dislocations, you will have a twist boundary. General grain boundaries can be viewed as a combination of twist and tilt boundaries. Thus, we can view that dislocations are the fundamental elements to build up these grain boundaries. There's one note to make here. If the misorientation angle is too large, then it's extremely difficult to resolve individual dislocations, because d, the dislocation spacing, will be very small. One common situation we can observe experimentally the dislocation boundaries is when we deform materials to a high strain level where it undergoes dynamic recovery. The GIF on the left is from Wikipedia. During deformation, especially at a later stage of deformation, dislocations will rearrange themselves to achieve a lower overall energy state. Such process is called dynamic recovery. If we have two dislocations on the same slip plane but with opposite signs, they will annihilate each other. If we have dislocations of the same sign but on different slip planes, they will stack on top of each other, which we have already discussed previously, and this gives us dislocation boundaries. In this example specifically, those are tilt boundaries. The formation of dislocation boundaries are affected by a number of parameters. The image here shows the dislocation structure of an iron sample deformed at room temperature. You can clearly see the dislocation boundaries or dislocation walls and dislocation-free interior. The TEM image here shows the same material deformed to the same strain, but at much lower temperature. Here, you don't see dislocation cell walls. The difference tells us the formation of dislocation boundaries is thermally assisted. Also, the stacking fault energy of the material can affect the characteristics of dislocation boundaries. In the first example, it's aluminum. Aluminum has high stacking fault energy and dislocation boundaries are quite sharp. In the second example, it's copper. Copper has medium stacking fault energy and the dislocation boundaries are more diffuse. The third example is copper-aluminum alloy, which has low stacking fault energy and planar slip prevails. The dislocation slip are more confined to their slip planes, resulting in a microstructure called Taylor lattice. In this video, we have learned the formation of dislocation arrays and dislocation boundaries are a result of dislocation motion and rearrangement. From next video, we'll start a new topic looking at the dislocation interactions with different microstructural features. The first one we'll look at is the dislocation interaction with grain boundaries.